Just like the torque, angular momentum also is an axial vector. It can also be split into the components along respective axes. The angular momentum about an axis say angular momentum is L about the x-axis, it is Lx, about y-axis its component is Ly, about z-axis its component is Lz. If you add these three components, just like the components of the ordinary vector, you are getting the net angular momentum. So, angular momentum can be split, can be divided into three components. Lx, Ly and Lz are the components of angular momentum along or about the axis x, y and z axis respectively. When you take the angular momentum of the particle with respect to the reference point, let the reference point have the coordinates x1, y1 and z1, and coordinates of this point mass with respect to the reference point, that be x2, y2, z2, and the linear momentum be mv, can be split into components mvx I cap plus mvy j cap plus mvz k cap. The position vector can be written as x2 minus x1 I cap plus y2 minus y1 j cap plus z2 minus z1 k cap. Just like the expression for the torque, what you did in the last section. You can write it x2 minus x1 as del x, y2 minus y1 is del y, z2 minus z1 is del z. And the linear momentum is mvx I cap plus mvy j cap plus mvz k cap. Or you can just write here, this is the component of the linear momentum along x direction px I cap. This is the component of the linear momentum along y direction py. This is the component of the linear momentum along z direction, that is pz k cap. One should know both the position and the linear momentum. The angular momentum of the particle about O is given as L is equal to R cross P. In tabulated form, I cap, j cap, k cap. Its x component del x, its y component del y, its z component del z. Its x component px, its y component py, its z component pz. When you expand the determinant, we are getting I cap into del y into pz minus py into del z minus j cap del x into pz minus px into del z plus kkf del x into py minus px into del y. So we are getting three components. This is the x component, this is Lx. This is the y component, this is Ly. And this is the z component, this is Lz. And when you add these three components, we are getting the angular momentum net measured with respect to the given point, reference point. Therefore, the angular momentum about a point can be written as the sum of angular momentum components about or along the respective axis. So, angular momentum about an axis may be a component of angular momentum about a point. Let me support this through an example. Well, let us take an example of a block which moves with the velocity v, and you are standing here. You are standing at the origin. This is the position vector of the block. The block is at a height of h with respect to the origin. Mass of the block is m. Find angular momentum of the point mass P about O. Find the component of the angular momentum of this point mass with respect to O along x direction, along y direction, and along z direction. To solve this problem, let us use the basic formula for the angular momentum of this point mass about this point O is equal to r cross mv. This is r vector, this is mv vector. The angle between these two vectors is theta. So we can write r mv sin theta r cross mv. Since the angle moves in clockwise sense, the angular momentum of this point mass with respect to this reference point must be clockwise. Here r sin theta can be written as h, height of the block with respect to the origin, mv into h, in minus k cap direction. So the entire angular momentum vector is directed along negative z direction. Therefore, along x direction, its component is 0. Along y direction, its component is 0. And along z direction, the component is mv into h. So angular momentum about an axis may be a component. Here it can be a component, or here it is a component. Angular momentum of the block about this point is entirely directed along negative z direction. So, angular momentum about an axis in this case is the angular momentum about this point O. Angular momentum about any point can be equal to angular momentum about an axis. In some special cases, as shown in this given example. The next context is angular momentum and the torque. We have to extend this idea for the group of particles. Before doing that, we need to clarify the basic meaning, the physical meaning of angular momentum and torque and their interdependence. Torque is the cause of change of angular momentum. When a particle experiences a net torque, its angular momentum changes. So, torque is equal to change of angular momentum with respect to time. Torque is equal to rate of change of angular momentum. It is equivalent to the case of the linear analog. Force is equal to rate of change of linear momentum. So, we can write F is equal to time derivative of the linear momentum and torque is equal to the time derivative of angular momentum about any point. If you take the torque, that must be equated with the time derivative of or rate of change of the angular momentum taken with respect to that same point. This can be written as the sum of the components. This torque about O can be written as torque about x-axis plus torque about y-axis plus torque about z-axis. This can be written as time derivative of angular momentum about x-axis, about y-axis, about z-axis in summation form. Generally, some cases or in general, we can equate the torque about any axis as the time derivative of change of angular momentum about that axis. Torque about x-axis is equal to time derivative of angular momentum about that axis. Torque about y-axis is equal to the time derivative of the angular momentum about y-axis, and torque about z-axis is equal to time derivative of or rate of change of the angular momentum about z-axis. This is a general view. However, through some examples, we can clear it, and some finer points we need to deduce by taking some suitable examples. So, here the context is a relation between torque and angular momentum. Whenever angular momentum changes, the particle must experience a torque. So, this is the equation. Torque about any point will be equal to rate of change of angular momentum about that point. We need to verify this formula by taking suitable examples. The example number 1 is the falling mango with velocity v, and at the same time it experiences a downward pull of earth. When it falls freely, when you release it from rest, it falls freely. It falls vertically down. So the line of motion and line of action both are same. Line of motion is given by the velocity and line of action is given by the force. Both the lines are same. This is the R vector, let it be B, is a constant quantity. The angle between R vector and mg vector is theta. Let us verify this formula. Tau O is equal to R cross mj, and already you have calculated that. This is mj into B, which direction? Minus KAB direction, proved earlier. This is the left hand side. The right hand side, if you take angular momentum about this origin, of this mango can be written as R cross mv. The angle between mv vector and r vector also is theta in this particular problem. In this particular example, in both the cases, the angle remains the same, that is theta, r mv sin theta. R sin theta in which direction? Minus KAB direction, or clockwise. Both angular momentum and the torque both are pointing in clockwise sense or in negative z direction, is equal to mv. R sin theta can be written as B minus KAB. You take the derivative of this angular momentum with respect to time. You are getting, all these are constant quantity, take them out of the derivative. Rate of change of the speed is equal to the magnitude of gravitational acceleration. I can write minus mgb into KAB, and that is none other than the torque experienced by the particle with respect to the given point is equal to tau O. Hence, left hand side is equal to right hand side. So, in this example, verify the formula tau O is equal to rate of change of LO, and we have verified it.